In section 12.4, we're going to look at some really valuable ideas related to something called the normal distributions. And there is such good information inside your book that I have grabbed a few paragraphs and some diagrams for us to talk about in this video. It starts out in your book and it talks about our heights are on the rise. In 1 million BC, they said that the height for a man was about 4 feet 6 inches, and that the mean height for a woman was 4 feet 2 inches. And then there's improved diets and medical care. The height for men now is 5'10", and women is about 5'5". And they say that the mean adult heights are expected to plateau or kind of quit changing in about at 2050. All right, and it shows in 1900 what they were, in the year 2000, and what they predict them to be in 2050 based on what's going on. All right, we're getting toward this normal distribution. Suppose that a researcher selects a random sample because they can't talk to every man on the planet, but they grab 100 men. They measure their heights and construct a histogram for the data. All right, let's look right here. All right, this is what it would look like. This is the frequency, the number of men, and this is the height. So there aren't any labels on here, but the mean, which is right here, would be probably that about 5'10". Okay, and so as you get much shorter, there aren't as many men, and as you get much taller, there aren't very many men. The frequencies go down on both ends. What they want you to see is, suppose that you increase the sample size. You don't look at 100 men, but maybe 1,000 men. You'll see that the shape continues to be very similar. Let's increase it again. Let's say we look at 100,000 men and we look at their heights and we have the number of men, so the frequency is up, and you can see that the shape is still similar, it's just getting more defined. Finally, what they predict is if you looked at all of the men in the population, you can't really do it, but if you looked at all the men in the population, you would approach a curve that looks like this. All right. Let's see. If it were possible to measure the heights of all adult males, the entire population, the histogram would approach what is called the normal distribution. And we looked at that a minute ago. The distribution is also called the bell curve, sometimes called a Gaussian distribution, named for a German mathematician, Carl Friedrich Gauss. All right, so this is what a normal distribution looks like. The normal distribution is a bell-shaped and symmetrical, meaning the right side looks very much like the left side, about a vertical line through its center. So this is like its folding line. Furthermore, the mean, the median, and the mode of a normal distribution are all equal and located at the center of the distribution. So if a characteristic, something that you're collecting data on, is what's called normally distributed over a population, then you can predict it will look like this. And the mean, the median, and the mode will all be the same. Going on, the shape of the normal distribution depends on the mean and the standard deviation. Standard deviation, it's back again. Remember, the standard deviation says how much the data values deviate from the mean. This figure illustrates 3 normal distributions with the same mean but different standard deviation. As the standard deviation increases, the distribution becomes more dispersed or spread out. but retains its symmetrical bell shape. So the light green one has a very small standard deviation. The values don't deviate very far from the mean. The blue one has a larger standard deviation, and the values do deviate a little bit more. The purplish brown curve has a large standard deviation, and it has data values that differ greatly from the mean. Nevertheless, they all have the same mean. They are all normally distributed. One last thing before we start looking at some example problems. When you have data that follows the normal distribution, you can always be guaranteed that approximately 68% of the data items fall within one standard deviation of the mean in both directions. Okay, so here's your mean, and one standard deviation this way and one standard deviation this way. You've got all these data values, and they all fall within one standard deviation. And that is 68% of all of the items. 68% fall in here. 95% fall within two standard deviations. Now that includes this portion in here. But within two standard deviations, you're going to find 95% of your data. And then finally, 99.7% of your data will fall within three standard deviations. Remember, we calculated standard deviations, and if the standard deviation is large, then you can imagine that this distance will be further and the curve will spread out more. All right, let's start with just some calculations, and then we'll look at some applications. All right, number one. All right, we have some information given to us. It says the scores on a test are normally distributed with a mean of 80 and a standard deviation of 16. What is the score on this test that is half a standard deviation above the mean? So what score is the mean plus 1/2, and I'm just going to say SD for standard deviation. I know that's not really the abbreviation, but it makes sense. All right, so the mean is 80 plus half of the standard deviation. That is 80 plus 8, or 88. So a score of 88 on whatever this test is half of a standard deviation above the mean. Let's keep practicing. The scores on a test are normally distributed with a mean of 90 and a standard deviation of 18. What is the score 1/2 a standard deviation above the mean? All right. So it is, again, they're saying the mean plus 1/2 of the standard deviation. The mean is 90, and plus half of a standard deviation, which they have calculated and told us is 18. That's 90 plus 9 is 99. Okay, let's look at this last one. It says the scores on a test are normally distributed with a mean of 150 and a standard deviation of 20. Find the score that is 1.5 standard deviations above the mean. Now, rather than using 1.5, I think I will use 1.5. Okay, so it is the mean plus, 1.5. Well, that messed up. 1.5 times the standard deviation. So that will be the mean is 150 plus 1.5 times standard deviation of 20. That is 150 plus 1.5 times 20 turns out to be 30, and we get 180. That is the score that meets that qualification. All right, now we're going to take a look at the 68, 95, 99.7 rule. So we've already seen and talked about the bell curve and how 68% are within one standard deviation on either side, 95% fall within 2 standard deviations on either side, and that 99.7 fall within 3 standard deviations. Almost everything falls within 3 standard deviations. There's just a teeny tiny bit of data, 0.3%, that falls outside. Now let's see what this question is. It says, the mean is 18, let me start at the beginning. Not everyone pays the same price for the same model of car. The figure illustrates a normal distribution for the prices paid for a particular model of a new car. By the way, I have seen an advertisement that shows this bell curve. All right, the mean is 18,000 and the standard deviation is 2,000. Use the rule to find what percent of the buyers pay between 14,000 and 22,000. Okay, I'm going to highlight. These are prices in thousands, and I'm going between 14,000 and 22,000. What percent are between those? Well, if I look up here, I happen to be exactly 2 standard deviations to the left, 2 standard deviations to the right. So for all of this region, for all these different prices for cars, what percent of the people buy those? And it is here. So it is 95%. The percent sign's already given. All right, let's look at our next one. All right. Once again, $18,000 is the mean value, mean cost, and the standard deviation is still 2,000. And it says, use the rule to find what percent of the buyers pay between 12,000 and 18,000. Okay, so I'm going to use my highlighter again. Between 12,000 and 18,000. Well, to me, that looks like this portion right here. So I believe it makes perfect sense that it will be 1/2 of 99.7%. If I take half of that, in other words, divide it by 2, I will get 49.85%. All you had to do is put in 99.7 divided by 2 and you'll get 49.85. That's the percent that is that group of buyers. All right, let's look at our next one. All right, this time the numbers have changed a little bit. We'll see how it affects things. The mean is 19,000 and the standard deviation is 500. Nevertheless, this rule still applies. And it says find the percent of buyers who pay between 17,500 and 19,000. So you simply have to find those, and they're never going to give you some that you can't find between 17,500 and 19,000. And this actually mimics the problem we just did. So once again, we're going to take half of 99.7% is on this side, and that is again 49.85%. So number 6 really felt like a repeat of number 5. Number 7. All right, we've still got the buying new cars. The mean now is 16,000 with a standard deviation of 500. And goodness, this is a little bit boring because we're doing something very similar again. What percent of the buyers who paid between 14,500 and 16,000? So I'm sorry, this really wasn't very challenging because it is that same thing again. This one, once again, is 49.85%. Okay, not a whole lot of fun, but you can use this to get different percentages. We're going to continue in this homework assignment, and we're going to talk about something called a Z-score. And a Z-score describes how many standard deviations a data item in a normal distribution lies above or below the mean. The Z-score can be obtained by using this formula. Take your data item, subtract the mean, and divide by the standard deviation. Data items above the mean have positive Z-scores, and data items below the mean have negative Z-scores. A Z-score for the mean is 0. Now, at first we're just going to practice finding Z-scores, and then we're going to look at some applications of how it can be useful, because we're going to use Z-scores sometimes to be able to compare data items from two different distributions. All right, so let's just practice finding them. We're going to use this formula. Get a little bit more room. All right. Number 8. It says, a set of data items is normally distributed with a mean of 180 and a standard deviation of 24. Convert 252, that's our data item, to a Z-score. All right, now remember, it is the formula for the Z-score is the data minus the mean divided by the standard deviation. All right, so in this case, it is 252 minus the mean, which is right up here, 180, and we're going to divide by the standard deviation, which is 24. And this would be written as Z252, written as a little subscript. And we subtract and then divide by 24, and the answer turns out to be 3. If you do this on your calculator, you could simply do parentheses. Well, there's a couple of ways. Parentheses, 252 minus 180, close those parentheses, divided by 24 is, and there's your 3. Another thing you could do, and I don't think I've shown this in the videos, you could take 252, whoops, you notice that I didn't use parentheses, minus 180, and hit enter to get the answer to just the numerator. Then hit divide by, and what it's going to do is take your most recent answer and divide it by whatever you tell it to, and in this case it's 24, and I still get my 3. Okay, so play around with it. There are different ways to use the calculator to do that. So I got a Z-score of 3. That means that the data item 252 is 3 standard deviations away from the mean. And in a bell curve, that means it's very far to the right. There's not much more out there, because remember, let's go back and look at a picture. This is the line, this is the mean. This is 1 standard deviation, 2 standard deviations, 3 standard deviations. So that score we just got was 3 standard deviations. It's way far away from the mean on the right side, on the big side. All right, let's go back. Let's now do number 9. We're just practicing finding z-scores. It wants us to find the z-score for 190, and let's see what the details are. The mean is 150, the standard deviation is 20, and my score is 190. So I'm going to take my data value, I'm going to subtract the mean from it, and then I'm going to divide by the standard deviation. So the score is 190 minus the mean, which is 150, divided by the standard deviation, which is 20, and that's going to get us 2. So this score of 190 is 2 standard deviations away from the mean, which is in the center of the bell curve, of 150. All right. Let's do some more. I'm not going to write the formula down each time. Z of 85 is 85 minus the mean, which is 80, divided by the standard deviation, which is 8. This gives us 5 divided by 8, and it says round to the nearest hundredth as needed. So this will be 0.63. If we did that on your calculator, let's move it over here, and we have 85 minus 80 gives us the answer of 5, divided by the standard deviation, which was 8. We get 0.625, but it said round to the nearest hundredth, rounds that up to a 3. All right, number 11. I want to find the z-score for 61. All right, it is the data, 61, minus the mean, there's the mean, 60, divided by standard deviation, which is 5. This gives me 1 over 5, and I'm going to get 0.2. That is not very far away from, that is 2/10 of the standard deviation. All right, for number 12, we're going to find a z-score for 60. So z of 60 is 60 minus the mean, which happens to be 60, divided by the standard deviation, which is 8. And that gives me 0 over 8, which is 0. And perhaps you even remember earlier where it said the z-score for the mean will always be 0. It said to find a z-score for 60, but 60 was the mean. So that should not have been a surprise. All right, let's look at number 13. We have a set of data items is normally distributed with a mean of 90 and a standard deviation of 6. Convert 72. Okay, so the z-score for 72 is, we will start with 72 minus the mean, which is 90, divided by standard deviation, which is 6. Because the value I was trying to find the z-score for is smaller than the mean, I end up with a negative z-score. And all that means is, if we go back and look at a bell curve, to be -3 standard deviations means you're way over here. Certainly doesn't have anything to do with this new car price, but just looking at the bell curve picture, it is 3 standard deviations would be way over here to the left. +3 standard deviations would be this side. All right, now let's look at an application problem. It says intelligence quotas on 2 different tests, so this is 2 different tests, are normally distributed. Test A has a mean of 100 and a standard deviation of 13. Test B, which is a different IQ test, has a mean of 100 and a standard deviation of 18. That means that this B, the scores are spread out more. Use Z-scores to determine which person has the higher IQ, an individual who scores 129 on test A or 134 on test B. So this is a use of the Z-score where you can find out, you can compare different tests with different means and standard deviations. These happen to have the same mean, but they wouldn't necessarily have to. So for test A, I want to find the Z-score for 129. Okay, that was the score on test A. So it's going to be 129 minus the mean of test A, which is 100, divided by the standard deviation for test A, which was 13. I calculate that. I round to 2 decimal places. Just, it doesn't say to, but I am. I get 2.23. Is the Z-score? It is 2.23 standard deviations above the mean. Now let's look at our test B. We want to find the Z-score for somebody who makes 134 on this test. Now normally people would just say, oh, 134 is better than 129. Well, these are different tests with different scoring. So we can't say that, but the Z-score is going to allow us to compare them. So it's 134 minus, and the mean of this one was also 100, and its standard deviation is 18. And this gives us a Z-score of 1.89. So, which individual has the higher IQ? Well, this one is 2.23 standard deviations above the mean, and this one is only 1.89 standard deviations above the mean. So the one with the greater Z-score has the score that is higher. All right, let's do one more. Ought to be very, very similar. So we have test A and test B. For test A, mean score of 100, standard deviation of 17. Then for B, it's 100, standard deviation of 15. And all right, somebody makes a 124. So I want to know the Z-score for 124. That's 124 minus the mean, which is 100, divided by the standard deviation, which for test A is 17. That gives me 1.41. So that score is to the right of the mean, 1.41 standard deviations over. Now I want to find a Z-score for a 131 on test B. So it's 131 minus the mean, and the mean for that test was also 100, and its standard deviation is 15. That gives me a 2.07. I'm doing my calculations off screen. Well, this is the larger. That means that the individual who scores 131 on test B actually had a higher score. All right, so you're going to be working with Z-scores. You've got your formula right here. It's on your handout. You're also going to be working with your bell curve and the 68, 95, 99.7 rule, and just a little bit of work with standard deviations and means. Okay?